this is what I was trying to get across. When I see this combination, I think danger. Watch out. Acid and potassium permanganate, very dangerous. Why? It's not necessarily H2. I don't know what's going to form. I just know that that's dangerous stuff, acid and potassium permanganate, because it's a powerful oxidizer. Because, I could look at my chart, or, I've seen the chart so many times, I already know, potassium permanganate and acid is nasty stuff. It's a powerful, it would be like the same thing. The potassium permanganate and the acid chemist convention is going to have the same handshake, because if they accidentally mix this with a good fuel or powerful reducer, you're going to get a violent reaction. Now think about nitrate and acid. Think back to Texas City. Nitrate and acid, is that dangerous stuff?
Yes.
Yeah, nitrate, that was an enormous explosion, the worst industrial accident in the U.S. What's stronger? Potassium permanganate and acid or nitrate and acid?
Nitrate and acid.
No, potassium permanganate and acid, right? I mean, you could look because the chart was given, but you could just see it there. What do you think? This is worse than Texas City. The only thing was there's fuel missing. So as long as we keep the fuel missing, this is like a predator, starving predator, like a whatever, like in Jurassic Park or something like that, if you've seen that movie. You got a hungry dinosaur looking for its next meal, what is it? What's going to be its next meal? Well, fortunately, I don't know if I told you, but I had one explosion in Chem 1B. A student did. A student poured ethanol into potassium permanganate and acid, and there was a loud bang and a huge flash. This was in the hood, in the waste jug. The student was making up a lab, and I mentioned to the student, don't mix that waste with the waste in the waste jug, because we were using powerful oxidizers that day, but in the previous lab we were using ethanol, which is a powerful reducer. And with the rush of the lab and making it up, the student accidentally poured, I don't know, accidentally or unintentionally, poured the ethanol into the waste jug full of, and they were a little bit short, so their head was inside the hood a little bit and singed their hair, like the front of their hair. Fortunately, they were wearing goggles, but the face was all red from the flash of that, and no glass or anything, just this huge fireball came out of the waste jug. And then ever since that happened, then I thought, this is a Chem 1B student. And I go through these chemical reactions, but it's just like they finish chemistry, Chem 1A and Chem 1B, without really knowing, chemistry. Chemistry is just chemicals and chemical properties, right? And so the other things have happened. Like there was one time I was driving. This was in Santa Barbara when I was there, and there was a tanker truck accident, and there's a whole bunch of brown fumes coming off. And on the news, they said, it was a tanker full of sulfuric acid. Sulfuric acid doesn't give brown fumes like that. What acid do you think it was giving off brown fumes? Nitric acid. It was nitric acid. Or maybe they said hydrochloric acid. I don't remember. But, hydrochloric, you treat hydrochloric and nitric acid totally different. Nitric, I would be a heck of a lot more careful with nitric, because it's a oxidizing acid. Whereas hydrochloric acid is not called an oxidizing acid. Yeah, and its oxidizing ability isn't nearly as great, something like nitric acid. And so I see combinations like this, hydrochloric mineral acid, but this is the acid plus permanganate combo is very dangerous. What do you think about acid plus dichromate? I think this stuff is looking for reaction. It's stable as long as there's nothing to react it with, right? But if you give it something to react it with, it's going to eat up the electrons, and what will it eat up? Well, oxalic acid. Fortunately, oxalic acid with hydrochloric acid and potassium dichromate shouldn't cause an explosion because oxalic acid is pretty well oxidized as is. It just has a little bit more to go until carbon hits +4. What's special about carbon in the +4 state? Well, it's lost all its valence electrons, and so it's not really going to react beyond that. So anyway, so when I see this, I think there's going to be a redox reaction, and what is it? Well, dichromate and acid, that's on the chart. You just copy it down from the chart, you know. It'd be dichromate plus 12H plus, no, 14H plus so many electrons. You just copy it down. But the problem is, what's going to become of oxalic acid? Where does oxalic acid go? And so oxalic acid is organic acid. A lot of these organics undergo combustion to form carbon dioxide. And so this was it. You know, the challenge was to know, to redox, to know that dichromate, you could just copy that one, but the half reaction for oxalic acid, oxalic acid is going to be converted to CO2, complete combustion of this, or complete oxidation. There doesn't have to be a flame. You know, and balance it, you know, as is, 2 carbons, 1 carbon, so change that to 2 CO2s, etc. So follow the same pattern that we had for ethanol. And how long did it take you to figure it out, you guys? How long were you working on this particular problem? Yeah, how about you?
I know it.
It was, you did it pretty quick? You knew it, okay.
You had the
All right. You too?
a few minutes.
Anita? Hmm?
A few minutes.
A few minutes, that's it? Okay. So, you know, it's that repetition of getting it into your long-term memory, and the repetition is, you know, just looking back. I think when I finished, you know, all my courses, my notes never were that thick, maybe like this. And then they're easy to go through, just over and over and over again. That's all I did. And then when it came to the final, I had everything. Actually, I had all this memorized when it came to the final, you know. And so it's good to have this memorized, because then on the final, I'll tell you, the final at UCLA, they're going to have one challenge, one very difficult challenge problem, you know, that, and if you don't have this framework down, it's very hard to solve sometimes. All right, so it wasn't meant to kill you. I did say, you know, that it was going to be maybe easy compared to if I had put in work, because conceptually work takes a lot of time to digest, you know, the definitions and the concepts. And so this is why thermo gives a lot of problems. So with thermo, it's especially important that you go over and over and over again so that you have those definitions down. That's what we're going to talk about today from behind schedule. Are there any other questions about the test? Is that enough? Just see the pattern. Since
regarding the 2 liter of the nitrogen, react with 1 liter of the oxygen to get the liquid water, right? So what's the final one?
0.036 was in.
How do we figure that
Yeah,
out?
how do you figure it out?
All right. I can just do that really quick. 2 hydrogens plus an oxygen, these are gases, yields 2 waters. Oh, I see. Did I say 2 liters?
You say 2 liters?
Yes.
So there's no answer.
Yeah, I was supposed to say 2 moles. Shoot.
Scratch it out.
All right.
Remember, I've been asking you this like 5 times throughout the test.
Now I see what you're asking.
Yeah, there's no way to get that.
Yeah. I thought I had fixed it from the last one.
No, it's 2 liters.
Oh, shoot.
No, the long dose.
And so what did you write? E?
The long dose, that's their answer.
Hmm? E, none of the above?
I changed it like 3 times and then I put 2,
Yeah,
thinking that it was
sure.
H2O gas.
Yeah.
Yeah.
Yeah, if this were H2O gas, then it would be 2 liters, right? But it's H2O liquid. And if I said, how many liters, if I said like 40, what was it, 24.5, 49 liters, 24.5 liters, then this should be 0.036 liters, right? If I did that. But I have much less than 2 moles, so I didn't get, 2 moles of water weighs 36 grams. 36 grams should be 0.036 liters, right? And so the answer should be E, none of these.
Can you accept a 2 for
Yeah.
H2O gas? Because in the question you said how much water forms, you didn't specify if you want liquid or gas.
Yeah.
Well, I said in the following reaction.
Yeah.
In the following reaction, it was specified as H2O liquid. Did you write H2O gas on the test? Did you write it as gas, 2 liters of H2O gas on the exam?
This is
Give it to us.
this question you should accept with both of those.
It would be a lot easier to accept if I just left it as H2O. Then, if it was left as H2O, we don't know what the temperature is, so it could be a gas, right? And then you're right, it would be 2 liters. 2, 1, 2.
Yeah.
But since I wrote it as H2O liquid,
It's partial pen, 1.5.
well, let me think about that. I see what you're saying. Right.
That was a tricky one. Oh, do you have the answers for the 5-point problems? The one with the coffee cup?
Yeah, which one?
The coffee cup?
The coffee cup?
What's the
Yeah.
final temperature?
Yeah. It's like 74.
Something like that.
Okay.
And on the
It
last
was in the
problem,
70s, uh-huh.
on the last problem, we had 50 milliliter of water and 2 grams of
That's true.
whatever.
Mhm.
Did we have to do 52 grams for the
Yes.
solution?
What if we do 50? Can we get half of
If you do 50, it's wrong a little bit. Yeah.
We need the concept.
Concept is
We
like.
don't understand the concept.
The concept is, the other part of the concept there is that the surroundings, what is the surroundings isn't just the water, it's everything that's left over. Everything that's left over includes the,
What was the answer in joules per gram?
actually, I don't remember. It was in the low 50s, I think. What was it, 50? Does somebody remember that?
My answer was around 2.
Oh, per gram? It was about 1,000 joules. And so it came out to about 40, that's right. About 40 kilojoules per mole.
Yeah.
Yeah, about 1,000 joules per gram, 40 kilojoules per mole.
But what if we
roughly.
put 50 there? Can we get some credit for that?
Yeah, that's, you'll get partial credit. But that's a common thing, actually, especially in experiment 2. It's very common that people will write 50 or they'll write 52 even if they're given 1.95 grams because the book says 2 grams, right? But what you actually got was maybe 1.98, 1.95, whatever they weighed out in the stockroom. Maybe it could have been 2.05, who knows? But you have to use the mass that you had.
And that's under the constant.
Oh, it was constant pressure.
Value.
Because
Yes.
the bulk of it was.
Well, it was constant pressure.
But there's no work done, so it can count under the constant volume also.
Right.
Because all the
Right.
joule.
Right, there's no work done because the system volume really didn't change
Okay, but it's like
significantly.
heavily insulated, something's constant value.
But the actual conditions it was done under would be constant pressure conditions, and it just equals constant volume. Because it wasn't done in a bomb.
So it's heavily insulated, so.
So you're thinking constant volume?
Yeah, because there's no work done.
All right, yeah, I didn't anticipate that, so.
The other one was tricky.
Anyway, the constant volume, constant pressure, that's not worth much at all, but I see what you're thinking. Heavily insulated mean isolated.
Yeah, and there's no work done, so I think.
Yeah, but, okay.
If you didn't put heavily isolated, I will.
If I didn't write heavily insulated, you would have
Right
written,
there.
all right, that's fine. All right, I'll take that. All right, anything else?
When will you have these graded?
Next week.
Take your time, be lenient.
Let's see. The thing that kills people on the equation writing is getting the formula wrong. If you get the formula wrong, there's not much partial credit for that. Uh-huh.
Like the question where you asked like which of these compounds are inherently unstable is ammonium nitrate. It's not inherently unstable.
Ammonium nitrate is inherently
It
unstable.
was all of them, right?
It was all of them, right?
Yes, you did it on the exam, practice exam.
See, I wasn't sure because the other three were
No, because you
soluble.
said N's are two different oxidation states, so they're unstable, right?
Right.
Yeah.
In the same compound, you just gotta get them close to each other. One nitrogen is -3, the other nitrogen is +5. You know, if this were tug of war, how can it sustain? You know, how could one nitrogen have 3 extras and the other nitrogen be missing 5? So that's inherently, in the same compound. Nitrate alone is not inherently unstable. If you had sodium nitrate, you would need a fuel to do it, right? But anyway, those are partial credit, so it's worth it's worth 2 points. So each one is half a point.
Oh, that's.
And so if you miss ammonium nitrate, you don't get the whole thing wrong. You just lost a half a point.
Oh, okay.
Okay.
That is awesome.
What was the one I asked you yesterday? The CO2?
CO2.
Combustible or not?
Oh yeah, CO2 combustible.
So,
And
you
then,
didn't think earlier.
well, you were asking, so then I said this.
Think about what burns.
Right, you said magnesium and CO2 burn, right? And
You
then,
said the metal will burn at
yeah.
the smell.
Magnesium and CO2 does burn because we showed the video. I showed the video of that. It does burn. But, you know, does oxygen burn?
No.
Or, well, it burns with methane. And so this is what I was trying to say at the
The
end.
trick is in combustible, yeah.
Right, like a combustible or flammable material. You know, you label it. Those would all be reducing agents. Yeah. CO2 would be an oxidizer. Combustible materials would be the reducers. So you need a reducer and an oxidizer. Fuel and oxygen, you know. Oxygen being the oxidizer. But you don't need oxygen. Any oxidizer will do.
So the answer is full, yeah.
The answer is, will it combust? No. No, it won't combust.
What goes with CO2? What did you say?
Magnesium metal. Did I show that video?
Yeah.
So you do not use a CO2 fire extinguisher on metal fires. CO2 is a weak oxidizer, but metals are strong reducers. And so it's the same thing. If I got metals around, I'm thinking, oh, okay, I got, especially alkali and alkaline earth metals, those are dangerous. And so it's the same thing. When I think about sodium, it's like the similar situation as acid and permanganate. You know, the sodium chemist. Did I tell you about the explosion I did?
No.
Was when I was using sodium metal. I had a big chunk of sodium metal. I was reacting it with some alcohol, and I had to do, because sodium reacts very violently with water. Did I show the video of that?
Yes.
Right. And so no water had to be present. So I was doing this in a glove box. The problem with the glove box is, you know, when you're doing reactions. I didn't talk about this already?
No.
When you're doing reactions, especially in organic chemistry, you have like a bucket of ice, you know, a container of ice water. You have a container of ice water because if the reaction starts to go, or start going violent, or start speeding up, you want to slow it down. And so you can cool it down rapidly, and then the rate slows down. The problem with doing it in the dry box is I couldn't have a bucket of ice water. Sometimes I put in some dry ice and acetone. Dry ice acetone makes a very cold bath, and it's used to cool things down. But this time I didn't put any. Instead, I put a big aluminum plate in there. You know, I thought, okay, the aluminum plate will radiate off the heat, and so the reaction started getting a little bit violent, And so, okay, grabbed my aluminum plate, put it on there, it did nothing. And then it started getting more and more violent. And the thing about reaction rates is they're non-linear. And so all of a sudden, it went from, oh, a little violent to explosion in like a couple of seconds. And it was, it's a big explosion, but fortunately, it was in a plexiglass box, a glove box. Everybody came running down to the lab to see what just happened, but I was okay. But the plexiglass just flexed out like this back in. It was, yeah, so that was my biggest explosion. Unintentional explosion there. So anyway, sodium's like that. You got to watch out for this stuff. And so I'm looking for any oxidizers. If I use a powerful oxidizer like acid and permanganate, you're asking for big trouble, right? And so you use a weak oxidizer. What's a weak oxidizer? Water is a weak oxidizer, right? Water is a weak oxidizer, and did you see the reaction with water? Yeah. And so you think CO2, just exhaling on sodium metal, is that going to cause some? Maybe, it depends. Water, the difference between water is the concentration, the density. Water is a liquid, CO2 is a gas. So CO2 gas is mostly empty space. So if I'm exhaling CO2 on this, I probably wouldn't worry too much. I wouldn't really see a big explosion. But CO2, maybe it's comparable to water. Maybe not. And so, here. React.
Why can CO2 be an oxidizer if it lost all its electrons already?
What's that? Why can't it be an oxidizer?
If it doesn't have any electrons.
Oxidizers, they don't want to lose any electrons. They want to take electrons.
Oh.
And so one of the products from this reaction, from the reaction of magnesium, was soot, the black charcoal-like particles that formed. And so the CO2 took electrons from magnesium metal to make soot particles. That's what happened in that particular reaction. Okay, what else before we leave that test? Nothing. Yes, I'll work on that.
20% O2.
What's that?
There's one question that was at 20% O2 gas.
Right.
50.
Right, so you calculate how many liters of O2 you need. It's like 41 liters of O2, pure O2.
Yeah.
But we're breathing air, so air, it's 100 liters of air for every 20 liters of O2. This would be Avogadro's type really ratio. That problem?
Yeah. So it was,
Yeah, so we went from grams of glucose.
yeah, those
Grams of glucose to moles of glucose.
Moles of glucose to moles of oxygen.
Yeah, to moles of oxygen.
And then
Moles of oxygen, then you could either go mole, because the volume ratio is equal to the mole ratio, which is equal to the pressure ratio. Right? But I went from moles of O2 to liters of O2, using 24.5 liters per mole, and then liters of O2 to liters of air. I was thinking not to make that one multiple choice, so I could see. It ended up,
There's many ways to do it.
there are many ways, yeah. You don't have to do it that way. Any way is fine. All right. Okay, let's talk about Chapter 7. Tomorrow's lab is actually Chapter 8 material. So I'm behind schedule. So what I'm going to do is I'm going to continue on Chapter 7 until I finish it, but in lab tomorrow I'm going to start Chapter 8, just enough so we can talk about the lab. That's it. I think we're doing experiment 3, is that right? Yeah. We're using a different piece of equipment, so you don't have to prep your notebook for tomorrow. I forgot to mention that in the morning class. I'll post it on the outside. So, we were talking about work last time, and how work can impact the amount of heat that's generated in a particular reaction. I'm sorry? Oh, real gas? Did we not cover real gases yet?
You just dealt with ideal gas.
Okay, I'm even further behind. And now much further behind because I didn't talk much about the exam this morning. Okay, I need to talk about real gases next. So let's talk about that. We left off talking about this, right? PV over nRT. PV over nRT should equal 1. Ideal gas. 1. And so if we're looking at 1 here, all gases should fit this line. It should just be linear, straight line, horizontal, right? But what we're going to see is real gases are going to deviate from that line. Sometimes the deviation goes down and then up, and sometimes that deviation just goes kind of up from here. And so where do gases behave ideally? I'll tell you, one place a gas behaves ideally is here. Right there. Right? This gas behaves ideally right here. Why? Because one of the factors causes the pressure to increase, the other factor causes the pressure to decrease, right? What causes the pressure to increase, let's say?
An increase in temperature?
At a given temperature.
Decrease in volume?
Decrease in volume.
No.
Yes.
The volume of the gas particles themselves means that 1 liter of gas is not 1 liter of empty space. And the bigger the gas particles in the gas, the less room there is to move, and the less room there is to move. Did I draw these little pictures earlier? Yeah, okay. The less room there is, the higher the pressure. The other one causes the pressure to decrease. What's that? Not the speed. Intermolecular forces cause it to decrease. Now, ideal gases have no volume and no intermolecular forces. Real gases have volume and they have particle volume, that is. The molecules themselves have a certain volume requirement, space requirement. And so here, this is a case where the negative error canceled out the positive error. I see this in lab sometimes. In lab, people get a perfect result. Why? Because they screwed up one thing really bad, and then they screwed up another thing, and they just so happen to cancel each other out to give them the perfect answer. This happens on exams too, because sometimes people say, I got the right answer. This is the right answer. It's exactly the same answer as on the key, right? Or my answer. But I said, no, because you made one mistake here and another mistake here, and they just so happen to cancel each other out. If they didn't, then they were off here and they were off there, right? And so it's one of these situations where there's a saying, a old cliche that goes with this, is that a broken clock is always right twice a day, right? But so anyway, where does a gas approach ideal behavior? It approaches it way down here. Now, if we look at this gas, it's right here. It's behaving pretty ideal. Otherwise, it's not. And so, under what conditions are these? Well, under the conditions, we're talking up to about 10 atmospheres. The scale's hugely blown out, and so, we're getting hundreds of atmospheres, thousands of atmospheres out here. High pressures. Eventually that gas will condense, because the pressures are too great to withstand. And so maybe from about 0 to 10 atmospheres, it might be okay, or 0 to, maybe I shouldn't go to 10 atmospheres. 10 atmospheres is quite high. Maybe 0 to a few atmospheres. Yeah, it's okay. And so most gases will behave ideal. And so I might have mentioned this earlier, but under ambient conditions, most gases behave ideally. Can you think of, under ambient meaning, 1 atmosphere and 298 Kelvin, can you think of a gas under ambient conditions that doesn't behave very ideally? Hydrogen is very ideal. NH3 doesn't behave so ideally. Helium behaves very ideal. Why does NH3 not? Because NH3 has very strong intermolecular attractions, intermolecular forces. It can hydrogen bond. The same thing with water, like steam. Steam under ambient conditions should be liquid water, not steam. Helium, on the other hand, behaves quite ideal because it has very weak intermolecular attractions. Okay, in addition, ammonia is kind of a big molecule. Helium is a very small atom. So, differences there as well. Well, anyway, so we see it's ideal, approximately here. One of these, throws it one way. So here, this would be the deviation due to IMS. And then this is the deviation. IMS will tend to do what? If there's strong IMS, it should lower the pressure or raise the pressure? Lower the pressure, because the attractions prevent it from. And so lowers, let's say, lower P, keep everything else the same. So P dips down. And then at high pressures, what happens? At high pressures, the molecules start to get crowded, there's less empty space, and we see deviations due to particle volume. Helium has very weak IMFs, so it'd be something like this, where it doesn't really dip down much.
What's the difference between particle volume and density?
Particle volume and
Density.
density
I know density is
are
something.
kind of unrelated. Yeah. Density is how many grams or what the mass of particles is in
Here.
the whole volume. In the whole volume, it consists of two things: empty space volume and particle volume. And so if I had 1 liter of gas, it wouldn't be 1 liter of empty space. It'd be mostly empty space and a little bit of particle volume. And so if you were to liquefy that gas, then you can see what the particle volume is more accurately. Although it wouldn't be 100% accurate because liquids have some empty space in there as well. Well, this is called the compressibility factor, and this you don't have to memorize or know. It just kind of gives you a gauge of how deviations occur with pressure here. It doesn't show temperature. We just keep the temperature fixed. So if we know that, we're dealing with a non-ideal gas under ambient conditions, very strong intermolecular forces, pretty big particles, then we probably don't want to use the ideal gas law. If I'm calculating, let's say I'm doing a calculation, I'm calculating the pressure of helium versus the pressure of H2O gas. And it's going to be under the exact same conditions. In fact, does the ideal gas law even care what the gas is? If I look at it, it's just nRT over V. It never asks me, is that moles of helium or moles of water, right?
Doesn't matter.
Doesn't matter. And so let's say we get the exact same answer. Did I already talk about this?
Yeah.
Yeah? If we get the same answer, will you treat the answers the same?
No.
No, which one would be more accurate? Helium or water? Helium, for sure. Helium is much more ideal than water. Okay, what can I do to make water behave more ideally? I could lower the pressure or raise the pressure? Lower the pressure, more empty space. And raise the temperature or lower the temperature?
Raise the temperature.
Raise the temperature. That means intermolecular forces are less significant at a higher temperature. All right, but if I'm working at ambient conditions with a apparently non-ideal gas, or if I'm working at high pressures or low temperatures, do I want to use the ideal gas law? No, I don't. And so we have alternatives to the ideal gas law. These, there are a number of them, you know, one in the homework, but there's only one in our book. The van der Waals equation for real gas. Where do laws usually come from?
Actual application to theory.
Now I have to be careful what you know, because when I did it, originally I did it, what, observation to,
hypothesis.
no, observation to pattern, trend. So we look for some patterns and trends. Well, we can look at how gas behaves, right? And then we come up with a law. When we come up with laws are typically mathematical equations that fit the pattern or trend. Have you noticed that? These have a couple of names associated with it. It's called an empirical equation, or empirical, this is probably not, formula or empirical law. You know what empirical means? Have you ever heard that word? Empirical equation, define it for me.
Most general.
Not most general. Empirical means to the scientist, it means based on, we call it based on observation. And so it's not based on theory, right? You have two things. You have things that are based on observations, that is facts of nature, things that are derived from theory. And the van der Waals equation is like this. All they did was, okay, it's not linear, right? It didn't fit. And so when they measured the pressure and the temperature relationship, it wasn't ideal. You know, this straight line. It was non-ideal. And so what did they do? They just got a mathematical equation to fit that. Now you can get a mathematical equation to fit this using what are called adjustable parameters. And remember we talked about the polynomial fit? You can fit anything to a polynomial. If you throw in extra adjustable parameters, you can fit any kind of pattern, like this. But that's dangerous because, you know, we know that each adjustable parameter should relate to something, you know, theoretically, some kind of physical property of the system. And so in this case, this is the equation that fits the pattern. It's P plus n squared A over V squared. V minus NB is equal to nRT. And so they just have two adjustable parameters here to correct the pressure and one to correct the volume. Well, these actually, even though these actually come from a little bit of theory here, because here, what is N? N's the same as that N, number of moles. V, the same volume. And so this is what fits the pattern, this kind of map here. But what is A? A is just an adjustable parameter. You know, you just tweak it until it fits perfectly. Get that R squared 1. Right? That's the goal. But it turns out that A actually means something, and that is A is related to IMS. So if the attractions are 0, you know, it's an ideal gas, then what happens? Well, A is 0, right? And if A is 0, then this term drops out and it behaves ideally. And so the stronger the attractions, the bigger the A, and the more the deviations. And so the stronger the IMS, the bigger the A, which means what happens to the pressure? As this term grows bigger and bigger, this term must shrink, and therefore the pressure decreases. And so we expect to see this. Stronger IMS should lead to a reduced pressure. And so we just look at the magnitude of A. Now helium should have a small a or big A? Helium. Small a, whereas something like water should have a fairly large A, yeah. All right, then we go over here and take a look at this one, which is B, NB. N is number of moles, and what do you think B is? B is what we call the molar particle volume. If you had a mole of particles, how much volume would they occupy? In other words, B is particle volume per mole, liters per mole. And so if you want to see what a mole of, let's say, CO2 molecules, what volume that would occupy, just take a look at the number of B in the book. And so these terms are usually gotten from experiments by just fitting the line. Well, anyway, that's particle volume. So as the particle volume, as B increases, then there's less empty space. In other words, as B increases, the empty space volume, which is V minus, V, this is the total volume. So the total volume minus the particle volume is going to give you the empty space volume, and the empty space volume decreases. What should happen to the pressure? Pressure increases. And so these are the parameters here. And so B as, let's see, the particle volume increases, B will increase, and therefore the pressure should decrease. Oops, sorry, the pressure doesn't decrease, pressure increases. An ideal gas, what is the particle volume of an ideal gas? 0. And so an ideal gas has 0 particle volume, meaning 1 liter of ideal gas is actually 1 liter of pure empty space. We know it's not 1 liter pure empty space. It can't be, right? Is there such thing as an ideal gas? No. There are things that get close, but there's no such thing as an ideal gas. If there's no such thing as an ideal gas, should we then eliminate? Because if there's no such thing as an ideal gas, the ideal gas law is always in error. It's never right. Should we go ahead and eliminate the ideal gas law? No. The reason is why? Why not? You know, because it's wrong. It's never right.
It's accurate enough.
It's accurate enough, yeah. It's close enough. It's fine. you do a few of these calculations and you go, you know what? Let's stick with the ideal gas law. Because this is a bit of a pain, because A, does that depend on the identity of gas? For sure. You know, A for helium is totally different than A for O2. Right? And the same thing with B. B depends on the gas. So each one of these is specific. You look up in the table for A and B, what A and B are. So let's do an example calculation for this. And someone have their book handy, or? Okay, thanks. Actually, back. Or here, I'll put that. Don't want to get black all over it. These pens will stain my fingers. All right, let's do a simple calculation. You know, let's do a simple calculation. I just want to calculate the volume of CO2. Did you guys already do this? Maybe, maybe not. I'm going to calculate the volume of CO2 at 12.5 atmospheres. At 12.5 atmospheres. If I'm at 12.5 atmospheres, what do you think? CO2 is a very ideal gas? No, not like helium. You know, CO2 is kind of big too. So I expect CO2 to deviate from ideal behavior. And at 12.5 atmospheres, I better start to worry, right? I'm not thinking this is very ideal. And so I'm going to do CO2 at 12.5 atmospheres and 286 Kelvin. Means that I probably should use the van der Waals equation. If I use the van der Waals equation, let's take a look. CO2 has an A of 3.61. 3.61 liters squared atmospheres. The the units have to work out. Liters squared atmosphere per mole squared. And then B is 0.0429 liters per mole. So a mole of CO2 molecules only occupies 42.9 milliliters of space, the particle of the molecules themselves. Okay, so let's go ahead and solve this. Go ahead and solve it. For B. I'll give you a couple minutes. Do you have it? No? Okay. You're usually very fast with the math.
What number is this?
I think it's number...
It's number 121B.
121. This is number 121 in the homework. You have it, Chelsea?
Do you have to gram or mole CO2?
It's 185 grams of
Oops, 185
Yeah, you didn't tell
grams.
us that.
185 grams. Sorry. I guess that would help. Why didn't somebody say something earlier?
That was somewhere in the units.
You could just do per mole, you know, what's the volume per mole? That's fine, do 1 mole. Is anybody close to solving it?
7.39.
7.39? How did you solve it, Sherry? Okay, this is
Yes.
a lot of work. Okay, tell me what you did.
Well, you solve for V in the PV NRT.
Okay, how did you solve for B in the PV NRT?
185 grams of CO2 times
Oh,
1.
what was V equal to? NRT over P?
Yes,
Okay, and then,
and then 185 grams of CO2.
okay, and then what was the volume now?
Oh, I'm sorry, 7.89 liters.
7.89 liters?
Yeah,
Okay. Is that what other people got?
but then that's, sorry, that's the ideal.
That's the ideal.
The other way I used, I'm sorry. I had to solve for volume for the van der Waals.
Okay.
So then, do you want the whole equation?
Oh, yeah. Well, what did you get it in the cubic form?
Yeah,
Okay. And then how did you solve the cubic?
and then you plug in the ideal into there to get the estimate,
Mhm.
and then just trial and error and use a quadratic to get the actual,
All right.
to get closer to it.
There are different ways you can solve this, so let's talk about that now. We don't have that much time. So one way that people solve this is to get it into cubic form. In cubic form, you have b cubed, av cubed plus b squared plus cv plus d equals 0. You can get it into the cubic. And do you guys know how to solve cubic equations? It's been a while.
Practically from both sides.
Well, one thing is you can buy a fancy calculator like mine, the Casio FX115ES. This calculator will solve quadratics and it will solve cubics. And so all I do is plug in A, B, C, D, and then it'll give me the answer. With a programmable calculator like a TI, no problem, right? No problem. And so technically you could use your calculator to solve this, right? Because these calculators are allowed. Right? The programmable calculators are forbidden.
Can you show us how to do it? Because
I'm not going to show you because I'm going to do it a different way. But to solve it, it's really easy, actually. It just asks you what is A, what is B, what is C. You just plug it in. I'll show you how to do quadratics later. But the situation is we need an alternate technique because what if we had a fourth order, you know? What if we had an AB to the fourth plus BB to the third plus dot, dot, dot. Now, will our calculator solve a fourth order equation? No. And so what do I do if I'm given a fourth order? Well, I have two choices. One, I'm not going to give you a fourth order. That solves the problem. Or two, you have to come up with an alternate method to do fourth order. And so what do you want to do? Do you want to hope that I don't give you a fourth order?
Yes.
That doesn't work. In Chem 1B, you'll get a fifth order, sixth order. You're not going to be able to solve these punching it in your calculator, right? And so the technique Sherry mentioned is the way we're going to solve this. And so I'm not even going to bother with getting the cubic form. I'm just going to leave it like that. I'm going to leave it like that, and we're going to use the method. The fancy name for this is called the method of successive approximations. The method of successive approximations is discussed in one of the appendixes. It's appendix, I forgot, the appendix A of your book. And the method of successive approximations is just a very simple tool that is being taught now in elementary school, which is good. It's called the guess and check. This is what they call it in elementary school. Have you heard of the guess and check method? So just guess a value and then check it. The guess and check method. We'll do a simple guess and check first. And so 2x equals 6. The problem is if your guess is a bad first guess. You know, if you did like, I guess x is 0.005386, right? And that doesn't work, and then you go to 0.005387, you know, and go on. So it could take a lot of time, but if you have a good first guess, then usually it doesn't take very long, and it's much shorter than doing this. And so like a guess here might be x equals 2, then we'll check it. You know, 4 is not equal to 6, right? Then we'll go to x equals 2.01. Should we do that? No, you usually take big steps. So you go x equals 4, and then we get 8, and then finally x equals 3, we get 6. So we're able to get it in 3 guesses, right? Something like that. And so we'll do the same thing with this particular problem. We're just going to do the guess and check method here. But we want a good first guess. Well, this is our good first guess. Typically, you know, it should be close to what the ideal gas law gives us, right? 7.89 liters, let's go with that. All right, now, I just leave it the same because we don't have to change it. It's just P is equal to n squared B, oops, not n squared, n squared A over B squared, B minus NB is equal to nRT. And so let's plug in the values that we have for this. What is the pressure? 12.5 atmospheres. What is N? How many moles? What was 180? Was that right? 185 or 180? 180? Grams? 185 grams? Divided by 4401 gives me 4.20 moles. So we got 4.20 square. What's A? 3.61? V? That's what we're trying to solve for, right? V minus N, 4.20, B, 0.04, what was it? 0.029. 429. And so what I do is I just try to simplify it as much as possible. And so I'm just going to have 12 and a half and then 4.2 squared times 3.61 is 63.68 divided by v squared. V minus, 4.2 times 0.0429 equals 0.18018 is equal to NRT. N is 4.2, R is 0.08206, T, what was the temperature? 286 gives me 98.5704. That should be enough. And so I set it up like this, and then I'll do the first guess. I don't want to, since it's just a guess, I don't want to punch in too many numbers. And so rather than 7.89, let's do a guess of like 7.9. Let's guess 7.9 and see what happens. And so V equals 7.9. What is the number? This should equal 98.5704. And so what I'll do is I'm just going to put in 7.9 squared, inverted, times 63.68 equals that, plus 12.5 equals this term, times parentheses 7.9 minus 0.18018.
What are our parameters? We're guessing and checking. We're guessing and checking around 3 ish set of parameters, otherwise it'll take forever.
I'll talk about that. We'll talk about that again. We got 104.3. Is that close enough? Should we keep guessing, or this is good enough? I mean, it's close, 98.5 and 104.3. Close enough for you? No, I don't think so. So what is close enough? Well, what's close enough is, do I need to go, there's actually more sig figs here. Do I need to go 98.5704? 00000? What do you think? No. And so the parameters are this. I want to know the volume, right? And so if I look at all the volumes, this is 12 and a half liters, so we're already restricted. I'm not 12 and a half, this is 12 and a half moles. And so it looks like... Atmospheres, 12 and a half atmospheres, sorry. And so it looks like, we were going to restrict ourselves maybe to 2 decimal places. And so what that means is there are a couple of ways we can deal with this. It depends on if you know what you want the volume to. If you need the volume to the nearest hundredth of a milliliter, we're okay here. We adjust this until we can get it as close as possible to this. The other option is we just keep going until we hit this, which would take forever. And so what you do is you look at the precision, because in order to keep going to hit this, we might be going 7.893621 liters. And then I'm going, oh, I'm so close. I'm going to go 7.893211 liters. And I'm going to get closer. Do you think that's very effective there? No, because already we got way too many digits here, and we still haven't hit it. So we're going to say, well, that's close enough. In fact, it depends on how many sig figs we want here. Sometimes people stop too early. What happens is sometimes people will go, okay, what do I ask for usually when I'm asking for something? I usually ask for, if there are 2 decimal places, let's say in the volume, or 3 sig figs total, then I usually ask for one extra. And so some people will get this to 3 sig figs and stop there, whereas if they got it to 4 sig figs, they'd come out to a better answer. And so I'd like it at least a 4 sig figs to get it a little closer. Does that answer your question? And so the same thing happens here. 2x is equal to 6. Well, it depends on how many sig figs I have in the 6, right? And so somebody will say, okay, I know what it is. X equals 2.9. Well, x equals 2.9, I get 5.8. Wow, it's close. Should I stop or should I keep going?
Keep going.
And so there's a bit of judgment there, and so you got to think about, how precise, what the precision is that you're expecting in the volume. We expect a little bit better precision than 1. And so I'm too big, so what should I guess next? 7.8. Go 7.8. And so I just do the same thing. I go 7.8 square, flip that times 63.68 plus 12.5 times parentheses 7.8 minus 0.18018. Oops, just did an error. Punching this. Does someone have it? I accidentally deleted it. 103.2. We're getting closer, but we're still way far off. And so what do you want to do?
Go lower.
Go lower. 7.7?
No,
7.6.
7.5.
7.5? Okay, let's do 7.5.
8.5.
So again, the same thing, 7.5 squared. $99.78. Still not low enough. Getting close. What should we do? 7.4. What do you get?
98.64.
98.64. What should we go? 7.3?
3.39.
38? 7.38? All right, let's try that. 7.38. Let me do this. Let's go on another minute. Let's see. 98.42. So we want to go 7.39. We're out of time. The other thing is you just keep going until you run out of time. That's the best answer you're going to get. What's that?
98.53.
98.53. Ooh, this is close. This is very close. So should we stop here, 7.39? No, we want to go at least, if there are 3 sig figs in the problem, we want to go at least 4 and get it as close as possible. So 7.395?
98.59.
98.59? Okay, now are we good enough? No, now we went to the 4th. Now we got to keep going until we get it as close as possible to the 4th. Now, should we go 5 sig figs? Probably not. We'll probably just get the best because, when we're getting to, this would be tens, hundreds, thousands of liters. Actually, thousands of, this is only milliliters. Actually, we could go more.
7.394 gives you 98.58.
7.394,
Yeah.
98.575. 98.575? Wow, that's close. So should we look at This is still a little bit too big, so should we go to 393? 7.393?
I would just use the other equation.
98.56.
98.56. We went too small.
Yeah.
And so it looks like it's going to be 7.394 unless you want to go to 5 sig figs. If you want to go to 5 sig figs, you can get it even closer. But eventually you go, well, that's enough sig figs, 6 sig figs, 7 sig figs. When you're adjusting it, that's, well. But you want to get it as close as possible. You need to border it, and so it looks like you can continue going. You aren't going to get it exact because that would take a long time, right? You just get it close. What other equation? Yeah, you could use the other equation, but what happens if I give you a fourth order?
Our calculators can solve for that.
This
Yeah.
fourth order? All right, then I'm going to give you a sixth order equation. The situation is you have to learn this, even though you might have a very powerful calculator, because somebody can think of something to defeat that calculator.
In this case, you went down by a factor of 1. It would be easier to be cross it.
Sure, whatever you want to do, to get it. I would go, yeah, you're right, I would have gone bigger, to see, but up to you.